Okay, welcome back. Now the demo I'm going to be talking about the Coriolis force and its relationship to weather patterns. We have heard when we were younger, we've all heard that weather patterns are different in the Northern Hemisphere and Southern Hemisphere. In the Northern Hemisphere, hurricanes and tornadoes, they swirl counterclockwise, right, this way. And in the Southern Hemisphere, tornadoes and hurricanes swirl clockwise. And also sometimes you've heard that when you flush a toilet, the bathroom toilet, it swirls counterclockwise in the Northern Hemisphere and then clockwise in the Southern Hemisphere, right? So although this is not exactly true, usually Coriolis force affects things that are larger, right? So it's more true, it's more related to weather patterns more than the flushing of toilets. Because the flushing of toilets has to do more with the inconsistencies and the way that the toilet is actually made. Right, so that kind of trumps whether you are in the Northern Hemisphere or the Southern Hemispheres. But if you have two identical toilets that are made exactly the same, they don't have any inconsistencies, no dirt on them, nothing accumulated near the sink, then it is true that toilets in the Northern Hemisphere or sinks in the Northern Hemisphere will swirl counterclockwise, and then toilets and sinks in the Southern Hemisphere will swirl clockwise. So you're going to see this. So the Coriolis force equal to negative twice the mass of the object times the rotation of the rotational angular velocity of the object of the surface that you place it on, cross product with the velocity of the object with respect to that rotating object. So the way that the Coriolis force is made is that you get an object rotating like a platform. So in my case, I'm going to have a platform like this, and I'm going to get it rotating counterclockwise or clockwise, right? So that if I get it going counterclockwise, you get your right hand and you curl it in the direction of the rotation of the object, and your omega vector points up, right? So now if I get a ball or something, and I start the ball over here, right? And I push it inwards, right? Inwards, radially inwards. What will happen? So the direction, basically you can think of it this way. This is a 3D picture. The direction of the velocity of the object is into the board, right? This way. And the omega vector is up. So then this equation is saying take the omega vector and cross product with the v, omega crossed into v, and you right? And then negative of that is going to give you the force, negative 2m omega crossed into v. Okay, so if that is true, what's going to happen as this thing is going into the board, it's going to feel a Coriolis force that way. Coriolis force. So basically the Coriolis force is in the same direction as the rotation of the object. So if it's rotating like this, the Coriolis force is in this direction. But in the meantime, the object is traveling like that. So when an object travels like that and you exert a force on it like that, its path looks like this. Its path goes like this, like that, swirls around, right? So if this is spinning fast enough, you could actually get this to go like this and spiral back, and that's how a hurricane is made, right? If I go very fast, then it's going to go like this and fall off the table, right? So it's just going to go like this, curve, and then fall off the platform, right? But if I go very slow, and if this is spinning fast enough, and you might cause it to actually go around, so it will actually go counterclockwise like that, okay? So now, if I get it spinning the other direction, right? Like this. So now, let's say it's spinning this way, okay, like that. So now, the omega vector is down, right? Omega is down. And let's say I push it inward, okay? I push it like this, inward again. So then the V is into the board, omega is down. Omega cross into V this way. You take negative of that, so that's going to give you the force, right? So this time the opposite is going to happen. The object is going to go like this. The object is going to go like this, and then it's going to curve this way. So this is exactly why weather patterns are counterclockwise in the Northern Hemisphere, but clockwise in the Southern Hemisphere, right? Because the way that the Earth rotates, it's like this. It rotates like this, counterclockwise. So in the Northern Hemisphere, it's like being on a platform that's rotating counterclockwise, right? But in the Southern Hemisphere, it's like you're basically right side up like this, So in the southern hemisphere, the opposite is true. You got to go like this, and if an object is rotating like this, but if you view the bottom go like this, then it's actually clockwise, right? So the Earth is rotating counterclockwise when viewed from the top. But if you view it from the bottom, it's rotating clockwise, right? So if you're living in the southern hemisphere, you should be saying the Earth rotates clockwise. Okay? If you're living in the northern hemisphere, it rotates counterclockwise. So let's see the video, and then you can get a better understanding of how this works. Okay, so then I can kind of start spinning this counterclockwise like this. Okay, get a ball going like this. Throw it inwards. You see its path? Okay, let's go again. Go like this. Okay, so you see how the path went like this? But then the reason also it falls off is that there's not much friction between the ball and the table, and it just kind of falls off eventually. Okay, what if I spin it clockwise? See that? How it went like this and went clockwise, then came back. So actually, it made a full circle before falling off. So there is your hurricane pattern in the southern hemisphere. Okay? Let's try that again. Okay, now I hope that the video has helped you kind of clarify a little bit more about how this pattern is developed. So even though the object is traveling in a straight line with respect to the table, but because the table is rotating with respect to us, that causes the overall path of the object with respect to us to look curved. But the path of the object with respect to the table is straight line. You see? So Coriolis force is almost kind of like you can think of it as an imaginary force caused when you are on an object that is rotating. You might be traveling in a straight line, but because that object is rotating with respect to another reference frame, there appears to be a force on you with respect to the stationary reference frame, which is making your overall path curved, right? So then this is how the weather patterns are created. Now, if the Earth wasn't rotating at all, how would toilets flush? How would weather patterns form? Not really, right? They might form just due to their internal motion, but they're not going to be as strong at all, right? On Jupiter and Saturn, weather patterns are a lot stronger because the rotational speed of the Jupiter and Saturn are a lot faster. They rotate once every 10 hours. Jupiter is the fastest rotating planet, so we would expect that weather patterns would develop much more easily on Jupiter. First of all, because it's a gaseous planet, it's huge, it's very massive, and plus its rotation is very fast. So the Coriolis force effect is a lot more because the omega of Jupiter is a lot bigger, and it's going to cause a lot more force, a lot more rotation, and much bigger hurricanes. Okay? Thank you very much.